Nu kaut kur tuvāk laikās. Nu kaut ko būtībā mums tikai tā. Ko vēl piesaņemt? Grābs to gribēs kaut ko. Labi, man jāatbaika. Tā. Nosaka 3 minūtes. Pati. Time to draw something, time to speak about something. And it's something, today my plan is to continue with distance protection. First, I would like to speak about input values. Let's see what we got. Our line, our fold, let's say fold at a distance of alpha per unit from the observation point. What kind of values do we have? We have, it's our bus, poles of the switch. Here we have voltage transformer. We will have A, B and C phase voltages starting from this. And we will have A, B and C phase currents. From this we need to construct resistance. We need resistance to compare, operate, no operate with the operation area or zone. If inside disconnect line it's fault, outside do nothing. It's good for us if this is line vector, if this distance will be of that line. It's good for us. Position 1, line to line fault. We have, let's say, A, B, C phase. Fault. A phase current, maybe returning B phase current, like this. And we have, I can show it with voltmeter, A phase voltage and B phase voltage. Fine. We need being alpha z line. What should we take as an input values? Here is our fault loop. Current goes, current returns. So, this voltage is UA minus UB. UA minus B divided by this will give us necessary resistance. Phase to phase voltage divided by current difference. This branch, it's thing I should note, but in distance protection there are two separate and independent branches. One, how to say, branch or set of precession flow is for phase to phase, and another line to ground, phase to ground. They are separate. They may share some calculus resources, but as a logical flow, they are absolutely independent. Same will be divided and divided by C. Same. In all time, it was three separate, absolutely separate devices. Now, much more complex thing. Let's say it's our transformer, ground, fault to ground at a distance of alpha. Here, if we start looking, very first, very raw approach, we have this resistance alpha Z1 and another part, ground resistance. Problem, this part is tricky. It depends much. It depends on soil, on geomagnetic activity. Have not worked. We need to eliminate ground part from the resistance measure. The resistance we compare with the operation region should be free from ground part. How it can be done? Let's say we have the system. I will simplify. Task my line. Earth fault at a distance of alpha per U%. How will schematics look like? A system, the transformer, this is direct, part of direct sequence. Of direct sequence voltage, my relay observes. Negative sequence of Z1. Negative sequence, here I will do small voltmeter. This is negative sequence voltage, my relay, or at a relay point. And another one, again, my transformer to the ground, EA of zero sequence, alpha at line, but be careful, it's a zero sequence. Resistance, connection point for zero sequence. This is common bus for zero sequence. connect this, connect like this. Here, a phase of direct sequence flow of 0 at a okay, simple 0 current. Here is my schematic. Voltage relay observed as a phase voltage will be OA direct sequence plus OA negative sequence plus 0. This. Current, phase current, will be EA direct plus EA negative plus E0. Voltage and current, if you simple measure them, what do we need to eliminate? Ground resistance. We need to eliminate this part. Actually, here I will get in red. This part from common voltage of 0 equals to 0 currents multiplied by alpha, that line of 0 sequence. We need to eliminate this voltage drop. We control this current and we control this voltage. We can get it because it's easy to create a 0 sequence filter. If we simple take relay as relay voltage divided by relay current, it will not work. We will get an error. But we can do one thing. K0. What's K? It's a compensation factor. It's zero sequence resistance minus direct sequence resistance divided by direct sequence resistance. This eliminates this lower voltage drop from the lower network. Here, two moments. First, direct sequence and negative sequence are assumed equal. It's okay, nothing. Line. There should be no difference at all. It's okay. But the second assumption is bit tricky. The second part assumes what? Voltage drop from the ground current is simple E0 alpha that line 0. 0 at point of relay. This is 100% true if line is powered from one end. If line has a connection on the opposite side, we own a bit shaky ground. If fault resistance is low, Again, it's okay because on metallic fault we can separate zero sequence schematic without any problem. To the left and right side of the fault, and this will be true. But if ground, if our earth fault is with transient resistance, and we have path for zero sequence on the opposite side, error is unavoidable. This how big is this error? I'll speak about it in short time. But at the first point, this formula of for ground faults, distance protection relies on compensated voltage and current. Compensation. What these are? Or full line resistance, or resistance per length unit. These values are or full resistance or line, or ohm per length unit, per kilometer, per meter, per mile. Don't make mistake. Okay. Now we know new values. I can take, I can start considering influence of transient resistance more detailed. When we know how distance relays are calculating fault resistance, let's come closer to reality. We have two sides. Line, fault, and ground fault with transient resistance of RF. We will see current I1 and I2 here from this voltage transformer. We will get our relay voltage. Fault was at the distance of R. Without is line angle, in case of RF 0, we would see at alpha that line this line point. This vector is RF, and here is point in case I2 is 0. Current from opposite side adds this one is I2 RF, additional component voltage drop from the current from opposite side adds additional resistance, and it's not all. This resistance may have virtual, it's not real, it's visible to relay imaginary part. In reality, itself, transient resistance is active. It's very, very low inductance. But angle shift between currents from system 1 and system 2 causes appearance of this virtual imaginary part, virtual reactance. I would like to show one good research. One of my students, hey, come on. Oh, here it is. It's a master thesis of Sergei Sheikin. It's called Transient Resistance Influence on Distance Protection. 10 years ago, this thesis was defended. Here, I would do at first all kind of I would like to wait this. Hey, come. Here is actual fault recording. It's from actual fault, cross William 1. B phase was fault. And here, this diagram shows active and reactive part of the transient resistance. Blue line is imaginary part, green line total resistance, and red line observable real part. Another fault recording. It's again 4 and 3. Point 3 fall on Tume-Kandava line. Here it note the growth of current. Trees are not burned instantly. So here is processing. Red line active part of transient resistance. Blue line observable to relay. It's not real inductance, it's observable to relay imaginary part of transient resistance. One more Tum-Protzen line. Again, active and observable, the blue line, observable imaginary part of the resistance relay. It's from the viewpoint of relay. One more, again, same stuff. We see imaginary part of the fault. Here, Valmy relay. Slow burn, then strike through. Strike through. Here. Another fault, again 3, slow burn till stable transient resistance channel forms. And again, green full resistance and blue imaginary part. Okay, I can go forward. Here is our model. This one, it's a result of modeling. What's what modeling? Regime when energy, power was imported from the opposite side. Angle between system assumed 60 degrees. And here are trajectories with this point of burning tree. How distance protection will see process when tree burns, observable resistance flies into operation zone. More distant fault on the next one, adjacent line. Again, see what happens. Real operational characteristic of protection, that what we will get, will be in reality downgraded. For here, fault in the instant zone, but relay will be triggered in the second zone. Here, from outside, no operation at all, comes in third zone and then travels to the second. Again, we will face delayed operation. And the higher is distance forward, the more serious is this impact. Where is the next one I need? Yeah, this one. Exporting mode. We are exporting energy. See? Now we kind of negative. In case we are importing energy, transient resistance has positive here, positive imaginary part, going outside of protection zone and causing delayed operation. Here we go downward. If in case we are exporting energy, most probable is negative, downgoing imaginary part. This can cause non-selective operation. One more. Here, fault in second zone. Here, you see this area. No, non-selective operation. First zone can be triggered, while fault is in the second. Here we have a danger of non-selective operation. Again, zero angle. Here we will see delayed operation. Again, danger of non-selective operation. Yeah. If you designing protection for areas where high transient resistance are expected, take care. Sometimes to prevent non-selective operation, negative slope of first zone may be required. It can be a problem, really. Okay, what's next? 1 second, I will show one more potential problem. Here we saw effect on transient resistance. Another problem, so-called in feed. We have a source and fault somewhere here. First line, second line. This problem is not a problem for the first one. Its effects or backup operation. Similar problem. We have current 1 and here we will have current 2. In theory, we should see something like this is F, this is X. This one is resistance of the first line. I will do some angle. And here is alpha ZL2. Here is fault place. So let's assume what it's inside our second zone. Here's our first zone. This point is for case P2 is 0. What happens when we take this current into observation? It causes additional voltage drop equals to E0 alpha ZL2. And it shifts observable faults forward. We will get here our fault. So this additional part is caused by voltage drop on, from second current of this line P. A backup operation of our protection will be effective. We will see fault what is really in our second zone, but it will move to the third. This effect is called zone shortening. Our effective operation zone will be short, or operation margin will be close when it should be. It can be a problem bit. Parameter what used to characterize this is called current distribution factor. It's a ratio between fault current and current observed by our protective relay. In case relay observes full current, it will be 1. In case, for example, currents are equal, it will be 1/2. We can calculate settings for network most probable regime taken into account most probable value of current distribution ratio. But it's a bit dangerous. Where it's dangerous? In case this source trips first, current distribution factor immediately rises to 1, and if we calculated our settings, assuming this source is operational, or it may be unavailable or something like this, we will see instant elongation of our zone and possible non-selective tree. So high care, you should be very precautious, taking into account real values of current distribution factor. Safer to assume its maximum value, meaning 1. If you would like, you are pushed by something to take lower value, so closer to network normal regime, when this source is operational, you should very careful check what happens if this protection trips first. Current distribution factor will instantly rise to 1. My view, taking this lower the factor, lower the 1, is dangerous. It's up to your risk and policy of your company. Current distribution factor. Next thing you should care about. Parallel lines. Fault. Our current. Everything fine. Not fine. There will be a second current, I2. Lines, they're parallel, are coupled with mutual inductance. This inductance change only zeros is real accountable in zero sequence. But through this inductance, there will be additional voltage drop at observable to our protection as increase in observable resistance. So mutual coupling in this causes observable resistance to go forward. Actually, it will go upward because this thing is inductive. Influence of, in such case, influence of parallel line shifts causes resistance to increase. So effective zone will be shorter. You need to take this into account. Remember, what voltage dropped from this current on output line increases observable resistance. Yeah. Be something, it's not important. So take a time on modeling and perform a calculus for the regime when, of course, it's for parallel line. The more severe case, you have two lines sharing the same tower system. In this case, it's mandatory. You need to check what happens. More mandatory. Here, influence is on non-trip direction. Resistance increases, so observable fault point goes out of zone. Now, more complex problem. See, we have also source here. More complex problem is like this. As I draw, see, maybe, okay, I will draw it once more. So we have system, two parallel lines, and source on the other side. Here is our fault. For this protection, fault is in the second zone. For near protection, fault, let's say A, B, C, D. For protection C, fault is in the first zone. So this protection trips first. After switch is disconnected, we will see I1 and I2. Again, here is mutual coupling in zero sequence. In this case, we will see something opposite. We will see decrease in observable resistance because current from the opposite side, we will see move toward. We will see actually what fault will go from the first zone to second, from the second to first. For our here it's fine, but same thing happens also for D relay. D relays through this loop sees this fault. If the source is small or not present at all, bad thing can happen. Fault for this relay may go into operation zone. So this should be checked. When you do this for reality, it's mandatory. You need to check what happens in so-called cascade operation or sequential operation. You need to check what happens when first switch trips. Because it's for this one, decrease of observable resistance due to this mutual inductance causes speed up in operation. It's okay, this fault is internal. For this relay, fault may go into operation zone and cause false trip. Should be checked what the selectivity between them remains. If it is able, if there is a communication channel, one thing is very helpful here. If you have communication network, trip signal from the far end should be sent to opposite instantly. It's good for system stability. It's good to decrease damage of the fault. So if one end disconnects, if you have communication network, signal to disconnect the opposite end is very welcome. And this prevents false operation of this relay. But check it. In such case, where you have parallel line, disconnection of the switch causes reduces observable resistance both for this relay and for this one. Modern relays have one measure to fight this problem of zone movement due to mutual inductance. Modern relays have ability to take zero current of parallel line. Modern terminal have so-called compensation channel for parallel line. High-end relays allow to take zero sequence current of parallel line and compensate this shift of resistance due to mutual inductance. If you activate this channel, be very careful with sign, with polarity. You can make things much worse. Good practice is not meant some outside fault. Take a control record oscillogram from outside fault, any fault, and check correct sign of compensation. Be careful. One more. One more thing with fault zones. Again, parallel lines. One of the line goes out for maintenance. Fault. What will happen? We have our current. Because lines are coupled with mutual inductance, we will see circulating current in disconnected line. It appears like some kind of black magic, but you will see current circulating here in disconnected and earth on both sides line. This current causes decrease of observable resistance. You will up to 30%, 10-15% is very typical, but up to 30% can decrease zero sequence resistance. This will cause misoperation of protection because resistance is lesser than you expected. In case line goes for repair, line is disconnected for repair, and earth on both ends, you need to change settings of your distance protection. It's mandatory, or it will fail. It's a mandatory thing. Observable resistance decreases. See, it's important to remember delayed operation can be, how to say, served with backup. Non-operation can be handled with backup. But false operation, non-selected, not handled. The idea, I knew, guys, okay, no problem, I disconnected line, auto reclosing will handle it. It's not a good approach. It's not the way to deal with customer, not the way to carry business. Assuming what we will operate on selector and we will disconnect customers, okay, we will reconnect them. It's not a good way of business. Okay, one more potential problem. Something like this. Line with partial neutral inductance. Here, current here we have problem. In such lines where you have partial, if fault is inside an area, you will see decrease in resistance and observable elongation of operation zone. It's problem, it's dangerous, it can cause false operation. If fault is outside, okay, what happened? Nothing. If fault is outside, you again in same problem. Fault here on this line. Oh yeah. For this fault, what will happen in this area? Decrease of resistance. In this area, Again, decrease of resistance. Good practice for such a line with Part2 is use is a compensation channels. I0 and this one should compensate. Good practice is a compensation channel. When here we in the same situation, cascade operation. By good relay with compensation channel. What else? What else? What else? What else? Deformation. Okay. What else? What else? What else? Yeah. One more potential problem can happen if you have the worst case. You have simplified substation on your line with transformers without switch, but it's actual also for simple line. So you have taps with transformers. At the moment line is energized, these transformers will develop inrush current. And first for saturation and goes down. Inrush current is not a sign. It contains exponential component and it contains higher harmonics. First, good relays are equipped with the filter preventing influence from higher harmonics. And for modern relay, it's good to have a safety check. If you have a high presence of fifth, seventh harmonics, relay characteristic should be switched to less sensitive or delayed to prevent false operation from this inrush current. One second. I just remembered what I forgot. Yeah. One more thing. Switch on fault. For it is highly, it's expectable. Sooner or later we will come to switch on fault situation. When we switch line after a closing and we have a fault remained. For distance protection, it's normal to have a counter branch of algorithm for switch on fault condition. All the relays had a function when switch is disconnected, the time delay relay is activated. And on connection moment for some up to 1 second for some time, time of second zone is 0. On modern relays, it's better to use separated fast zone activated for short time after it's active when switch is disconnected, and it's remain active for 1 second after switch is connected. It's a best practice for switch on fault. And now one more problem. It's a problem of blind zone. Blind zone problem fault voltage available to relay as a function of distance looks like this. We always will have some minimum voltage, lower threshold where relay logic can calculate resistance. Precision, limit of precision. This means what at the beginning of the line we will have so-called blind zone, non-sensitive zone. We need to do something with it. First thing done with relays, it's a function of memory. Relays do remember, even old analog relays, do remember at last direction of voltage before fault. Old relays had resonance counter powered from the third phase voltage. In case there is not enough voltage, for example, AB voltage is too low, relay use a signal from this resonance current powered from C phase. It actually distance relay in such regime, how to say, degrades to directed overcurrent protection. Modern relays do keep value of voltage before fault, and it can be used to determine direction. But there is problem with precision. A real problem when we what happened? People worked on line, remain earthing, protective safety earthing remained, and line was switched on. Switch on fault. In this case, you seriously wait, I'm ending. So, in this case, there will be nothing in memory, and protection will not operate. Really. For such case, it's mandatory to equip distance protection with backup overcurrent protection. This backup overcurrent protection should be activated only for really should be activated for small period of time after switch is operated, while memory of main distance protection is empty. and on switch on fault condition it cannot operate. It's a kind of weak point of this distance protections. Switch on fault condition. Also, I will repeat, distance protection are vulnerable on power swings. Let's say some connection between systems. In case of serious problem, the loss of synchronicity, one. We have a severe condition in our system, it's lost synchronicity. The frequency on the one side is not equal to frequency on the second side. It's possible. Here, the point where the voltage is zero, it's a center of swing. Electrical swing center. At this point, for distance protection, is a free-phase fault. It will be inside an operation zone, and we will get false trip, false line disconnection, making problem more severe. To prevent this, typical now industry standard is discrimination between real line fault and electromechanical transient by speed on which observable fault resistance, event 1, event 2, time space between outer and inner merging trip defines first derivative of the impedance. This system works well, but if you have problem with burning tree, decreasing transient resistance, it may decrease slowly, and check seriously on the base of statistics. This one and better. What's the difference? These synchronous swings are symmetrical. E0, nearly zero. Fault with RF, triple E0 equals to E4. Meaning what you need in your relay logic, unblocking should be not only by the Z by the T, but also by the criterion E. Negative and zero sequence are present. This will prevent serious problem, non-operation of protection, because it's blocked by synchronous locking, synchronous swing locking mechanism. Okay, how many viewers? Few viewers. I think it's enough for today.